Okay, good morning everyone. So it is our third lecture and it is to continue section 4.9 and it was about spring mass motion. And we said in the last time that if you go with M to be the mass and K to be the stiffness for the spring, stiffness for the spring, yeah? So let me just remind you what is going on here. So we have a spring, yeah? And on the end of that spring, we have a mass here, right? So this is M, and K is for the spring, right? Okay, and we have also V, or we call it damping constant. And then the spring mass motion will satisfy the following second order differential equation, which says mass times acceleration, d square y over dt square. What is y? Just to tell you, so if this is y equals 0 here, yeah, y equals 0, then you are stretching. Say I'm stretching up to here, yeah? So you are stretching up to here, then y is this displacement. And here we said we're gonna arrange things in the following order. So you're gonna have the damping constant times the velocity, and the velocity now is dy over dt. So it is the derivative of the displacement. And then the last thing is the stiffness for the spring times y. And this could equal an external force like a magnetic force or maybe an electrical force, so F external. And in all our cases for this section, in section 4.9, I will always consider this to be 0. So always I'm going to have homogeneous case. Yeah? Homogeneous case. Now last time I give you one simple case, so a simple case. And this simple case is the following. We call this undamped motion. Undamped motion. Or some people call it free harmonic motion. So in this case, you know what is going on here. B, in this case, you consider assuming B to be 0, and F external is also 0. This is always the case. Always we're going to have F external equals 0. And in this case, you know that equation, this equation will become the following: md square y over dt square plus ky equals 0. And if you solve this thing, you know, if you solve this thing, then you need to change it to mr square plus k equals 0. And last time we said if you solve for r, then r will be plus minus square root of k over m times r. Yeah? And last time we said we're going to call this thing omega. Yeah? And in this case, your solution will be, solution will be the following. The solution for the simple case will be the following. It will be y of t equal to C1. Because alpha is 0 and omega is the same as beta, then you're going to have no exponential term. Yeah? You're going to have a pure trigonometric function. So omega t plus C2 sine omega t. Yeah? Now, you can change this form to another form which says y of t will be amplitude A, the amplitude A, and then sine omega t plus phi. Yeah? And I give you a rule how to calculate A. It was the root of C1 squared plus C2 squared. And if you like to calculate phi, then phi is just tan inverse of C1 over C2. And you need to be careful here because last time I didn't say this. You need to be careful when you calculate the tan inverse because you need first to plot. You need to plot the C1 and C2. So imagine that this is X and this is Y. So C1 is going for X, for example, and C2 is going for Y. So if you have C1 and C2, for example, if you have something like here, so here C1 is negative and C2 is positive, then you need to go and calculate phi using pi minus whatever calculated here, tan inverse, absolute value. So for this case, for example, tan inverse of absolute value of C1 over C2, right? We're going to come to this. I will solve a problem on this later, and I will tell you the story of calculating phi when you have C1 or C2 negative or both negative. Then you need to go to the right quadrant in the plane, and then be careful in choosing your phi. Now let's go for, this is the simple case, undamped motion. Why you called it undamped? Because you have cosine and sine. And the motion will be, so the motion, if you look here, it is better. The motion is sine forever, right? So sine continue forever. So let me go with the second case. The second case is when you have a damping force. So now here damped motion. Yeah, and for this thing, m d square y over dt square plus p dy over dt plus k y equals 0. We said we're going to always take the external force to be 0. Now here I'm considering the case when p is not 0. Yeah? So we have a damped case. Now again, if you go and change this equation to characteristic equation, we call it characteristic equation or second order algebraic equation. So you get PR plus A equal 0. When you solve for R, then you get the following. You get minus P plus minus square root of P square minus 4 M K over 2M. This is the rule for quadratic algebraic equation. So this is the rule. So minus P plus minus P squared minus 4 times M times K. Now there is some cases for this one. So let's go. So we are studying damped. Yeah? But for damped even, there is 3 cases. So case A. Suppose that you have P squared minus 4mk, which is the discriminant, right? I can call this the discriminant. I can call it delta if you like. So if this thing is greater than 0, what's going to happen? If this is greater than 0, then you don't have complex roots anymore. You're going to have real roots, right? Then you're going to have R1 and R2. So I said we can call this delta, the discriminant, or D. And now you have R1, right? R1 will be minus, so let me write here 2. So we're going to have 2 real roots, right? And you know this is R1 and R2. So when you go for R1, for example, it is minus B. Let's say here. So let's go R1 equal to minus B plus square root of B squared minus 4AC over 2M. Sorry, not AC, it is MK. MK. Good? And you have R2. R2 is just minus B minus square root of B squared minus 4MK over 2M. Good? One with plus, one with minus. This one gonna give me Y1, right? And this one gonna give me Y2. The solution number 1 for homogeneous. Then this one, if you like, this is here. This is alpha, right? And this thing here is, there is no alpha and beta, sorry, there is no alpha and beta here. It is real roots, sorry. It is real roots. So no need to cut this, it is a real root, but it is a number. Then I'm going to say solution number 1 is just E R1T, and solution number 2 is E R2T. And I can combine the two solutions to get the homogeneous, which is the general solution. It is C1 ER1T plus C2 ER2T. Do we have sine and cosine in this when you get real roots? So I have, do we have sine and cosine? No sine and no cosine functions. For this reason, then you don't have harmonic motion. You don't have a harmonic motion anymore. So if you go and graph this thing, for example, if you go and graph this thing, you may have a graph which looks like this. Yeah? Yeah? Now, in this case, we call this this case is